A warm welcome everyone here in the Blauwe Zaal. My name is Lucas Asselbergs. I'm head of Studium Generale. And this is really a very special program today because normally we don't have speakers like the one I will announce later on because this is a very special occasion because the person that's going to speak is going to receive a very special award, and for that reason she is in the Netherlands, and what a luck that is for us to have her here in our Studium Generale program. She will receive the Sickens Prize, and that will be given by Bernard Kolenbrander, the professor who's also the chair of the art committee. And that prize is given to any artist that makes really wonderful, colorful paintings or artistic works. And the work that will be discussed today comes from Cosmos. It's the result from a really interesting trip from the Cassini to Saturn, one of the most brilliant planets that we have in our neighborhood. So the program will be, there will be a lecture that will take around 40 minutes. Then there is room for people to leave the room because they have obligations elsewhere. And then we continue the program afterwards for the ones who will be available until 2 o'clock. So that's what we arrange, and that's what you can do if you have to leave earlier. But now, without further ado, I would really like to announce and give her a warm round of applause. Carolyn Porco. Here you go.
Thank you very much. Thank you for that lovely introduction. 32 years ago, the United States and Europe joined hands and took off on a spectacular adventure together. It was a robotic interplanetary mission called Cassini, and it was launched with the goal of exploring the planet Saturn. And it called for a long-duration, comprehensive, in-depth examination of everything in the entire Saturnian system. The planet itself, its magnetosphere, its enormous system of rings, and of course its collection of many moons. Cassini spent 13 years in orbit around Saturn. And that's nearly half of a Saturnian year. And it ended its life in a dramatic finale 5 years ago, burning up like a meteor in the atmosphere of Saturn. We're going to take a retrospective look this afternoon at our time at Saturn, remembering what we found there and some of what we learned. And then I'm going to conclude with what I think will be the enduring legacy that this profoundly successful mission is going to leave behind. Cassini was launched in the year 1997 and took 7 years to cross the solar system and finally arrived at Saturn in the summer of 2004. The main engine on the spacecraft was used to slow down the acceleration of the spacecraft so that it could be captured into Saturn orbit. An event that is artistically depicted here. And once in orbit, its tour of the Saturnian system began, unfolding as a complex trajectory of changing orbits that allowed views of everything that we wanted to study from a variety of directions. And it was this trajectory design that was at the heart of our success. Because if you're in orbit, you have the luxury of discovering something and then being able to modify the planned trajectory at some future time to go back and have another look, and in some cases, many looks. And it all worked like clockwork. It was really, it was the heart of our success. One of the main objectives of the mission was, of course, to study the planet itself, in particular its meteorology, and that means its wind speeds, the life cycle of small-scale storms, and the role of atmospheric eddies and the dynamics of the atmosphere and so on. And it just so happened that while we were there at Saturn, in late 2010, we witnessed a major meteorological event in the life of Saturn, and that was the birth of a huge lightning, thundering storm, the kind that you see on Saturn every 20 or 30 years, and the largest ever observed by a nearby spacecraft. We observed this monster storm be born, develop, and eventually fade away. And with all that information in hand, we've had the opportunity now, of course, to study it and try to understand it. The best explanation that has been proposed so far of what produces storms like this that only occur every 2 or 3 decades is that water, which is the constituent of the lowest cloud deck in the Saturn atmosphere, actually suppresses convection in the lighter hydrogen atmosphere for periods of decades until finally buoyancy wins out over gravity, and a large convective storm outburst occurs, just like a volcano going off. And so we had the opportunity to be there. It was really very fortunate. Then as spring marched on in the northern hemisphere, we saw in great detail a feature that had been discovered by the Voyager mission some 3 decades earlier. That is a feature called the Hexagon. And this hexagon is wrapped around Saturn's North Pole. All told, it's about 2 Earths across. And winds in this hexagon that blow at 220 miles per hour. And there's so many people, members of the public, who thought this hexagon was very, very strange. Whenever we posted anything on our website about this hexagon, our hits went through the roof. I think people thought it had something to do with crystal energy or something mystic and so on. But really, this hexagon is nothing more than a jet stream. It's just like the polar jet stream we have here on Earth. 6 conjoined waves with the head of one becoming immediately the tail of the one before it. And the only reason why this is so stable is because in Saturn there's nothing to run down atmospheric systems. On the Earth, atmospheric systems blow over the ground, over mountains, over oceans. That adds friction. The friction runs down the system, and then it just gets going again from start, some later time, some other place. But on Saturn and on the giant planets, there is no such friction. And once storms get started, they can last and be very, very stable. And so it is with this hexagon. Observations of phenomena like giant storms and hexagon and so on help us figure out what in the atmosphere of a giant planet is similar to and what is different from our own atmosphere. And the more that we understand about other planets or the processes that shape planets, the better custodians we can be of our own. Next, of course, are the rings. The rings are what makes Saturn the icon among planets that it is in our solar system. And they consist of countless icy bodies that range in size from the largest, this is of any significant number, the size of small apartment buildings or big houses, all the way down to the size of powder, tiny, tiny bits of powder. And these are all these particles are in independent orbit around Saturn. And the rings, of course, are big. It would take light, the fastest thing we know, 1 second to travel from one end to the other, which means that these rings from one end to the other would slot in very nicely between the Earth and the Moon. And the rings are very thin. They're only about 1 to 2 stories in a modern-day building, so they're probably no more than the height of this room. And the particles that compose the ring are traveling at high rates of speed around Saturn, about 20 to 40,000 miles per hour. And yet the relative motions of these particles is only like millimeters per second. So if they collide, they're colliding very gently. You can think of this as kind of like cars on a freeway. All of them are screaming down the highway, but relative motions are much smaller. And all these particles, because they don't collide violently any longer, all the violent collisions died out a very long time ago, because of that, they're very, very thin. And you can see that here in this depiction. I mean, that's actually a picture. It's not an artistic depiction. And one thing that you should note is, despite the fact that the rings are so large, if all the particles in them were collected together to compose a moon of the proper mass density for the Saturnian system, that moon would be no bigger than this little moon right here. So you get a fantastic, spectacular display for very little, well, comparatively little mass. And the rings exhibit an incredible variety of structures. This is and the structure, in fact, was discovered by the Voyager mission in the early 1980s. And we, of course, with Cassini, got the opportunity to go back and study it and try to understand it. This is a natural color image of the rings that we took with Cassini very early on in the mission. In fact, before we'd gotten into orbit. The rings, you might know, are given different names, A, B, and C rings. Astronomers aren't the most clever about naming things. And the rings have very different characteristics, one to the other, A to B to C. We don't quite understand why that's the case, but we have, with Cassini, had the opportunity to study and to learn more about what makes the rings structures on smaller scales so complex. For example, we know from Voyager, we know that there are many features in the rings that are produced by gravitational interactions between the ring particles and moons that are external to the rings. And there are almost all the features you see in this A ring are produced through an interaction with an external moon. But we have found with Cassini that the most dramatic structures that we've seen are actually produced by moons that are embedded in the rings. And I'm going to point out to you this gap here, which is called the Yankee Gap, and there's a little gap right here called the Keeler Gap. And we first saw in great detail what kind of structures these embedded moons could create during the Saturn orbit insertion maneuver that I showed you an artist version of later, when we were gliding very, very close across the rings, and we had our cameras pointed down, and we were taking pictures as we went. And I could tell you this picture completely threw us for a loop. This is the Yankee Gap, and we knew ahead of time that there was a moon in it, but we got to see for the first time this moon called Pan. And you could see the work done on the edge of this gap, all because of the interactions with Pan. Not only do you see these waves in the edge, but you see these streamers that are produced also by the work of Pan. These are the kinds of features in the A-ring I told you about that are produced by external moons. So this was very exciting to see what Pan can do. And later on in the mission, at the very end, we were very close to the rings again and got the opportunity to take a closer picture or two of Pan and look what it looks like. Okay, this is a moon that has a skirt around it because it is embedded in the rings, and ring material falls, because of gravity, falls on to this moon, but because the rings are very thin, it only falls around the moon's equator. So it's not every day you get to see a moon like Pan. And then in the gap next door, the one I told you is called the Keeler Gap, we had found, with Cassini, we'd found a small moon there called Daphnis. This moon is about 8 kilometers across, and we knew that it too made wiggles in the edges of its gap. This image was an image taken, like I said, at the end of the mission, but we had known of Daphnis' presence. We knew it created waves. This just showed us what those waves look like up close, and even a little streamer of particles right there. But during the equinox, when the sun, as seen from Saturn, would travel from the southern hemisphere through the northern hemisphere, the equinox occurred when the sun was directly over the equator. So the angle of the sunlight was very shallow, and that was a geometry in which anything protruding above the rings would create enormously long shadows. And that's when we found out that these waves created by Daphnis are actually towering walls of rubble that go up in the air 2.5 miles high. And We have since found out that the reason for that is because Daphnis, we don't quite understand why, is on an inclined orbit, and sometimes it's above the rings, and then sometimes it goes below the rings because it's inclined, and it's because it actually has a vertical excursion above and below the rings that it draws the ring material out of the plane, and that's why we get these spectacular waves. I love thinking about being in a shuttlecraft, flying across the rings really low, this gleaming disk of debris, and you're flying along and you're flying along and you come upon a wall of rubble that's 2.5 miles high. That needs to go in a movie. And in fact, one of my artist friends, Michael Carroll, actually put it on canvas. Okay, so speaking of moons, Saturn is accompanied by a very large and diverse collection of them. The skies of Saturn are literally dotted with moons. There's now over 80 of them. I've just shown you the very smallest, but in fact, they range in size from a few kilometers all the way to the largest moon, which is about, the size across is about similar to the US. And on Cassini, our goals were primarily to study the moons within a few million kilometers of Saturn. And these moons, in being all in the same plane, all formed at the same time from the same planet or the same parent nebula of material around the same planet, and moving around Saturn all in the same direction, they are kind of like a miniature solar system. And so we studied them the way you would a solar system. And through it all, we took some spectacular pictures. I'm sorry, because this presentation is rather short. I can't show you all the great pictures we took, but here's just some of them. Here is the moon Hyperion, okay, looking like something you would have pulled out of the ocean, except this moon is 2 times the size of the Netherlands. That is about 7% the size of our moon. And we know actually what causes Hyperion to look like this, but because I'm in a hurry, I can't tell you. And here's another beautiful image we took soon after getting into orbit. Here are the rings of Saturn. You're looking beyond the rings at the shadow-draped northern winter hemisphere of Saturn. So these are actually the shadows of the rings. And here is the moon Mimas. Okay, and here's another look at Mimas, which is Saturn's Death Star. It's about 400 kilometers across. It's obviously very cratered. There's no evidence whatsoever of internal activity on Mimas. We do know, we knew this from Voyager, that the projectile which created Herschel crater here came very, very close to smashing Mimas to bits. But Mimas won out. And then, of course, there's Saturn's largest moon, Titan, which is 50% larger than our own moon, again, about the size of the US, and the greatest single expanse of unexplored terrain that we had remaining in our solar system before Cassini got there. This moon gave us some of our most beautiful, most arresting images. Here's an image that looks like might have been a painting by the Russian artist Kandinsky. We learned from Voyager that Titan's atmosphere is compositionally very similar to the Earth's. It's mostly molecular nitrogen, but it is different in very important ways. First of all, it has no free oxygen, and it is suffused with small amounts of simple organic compounds like methane and ethane and propane. And these compounds can do 2 things. First, they form a 200-kilometer thick haze that completely envelops the planet, the moon, and they can be liquid at the surface, despite the fact that the temperatures on the surface of Titan are minus 185 Celsius. And this condition raised the very exciting expectation, even long before Cassini got there, that when we got there, we would find bodies of liquid hydrocarbons on the surface. So think a basin the size of the Mediterranean filled with paint thinner. That's what we were expecting to find on Titan. So consequently, Exploring the surface of Titan and its surface environment with Cassini were major objectives for us scientists. And for this reason, Cassini carried instruments that allowed us to penetrate through the haze and see down to the surface. And one of those instruments was a radar instrument. Has no trouble, seeing things through clouds and haze. And also, we equipped our cameras, which are really like telescopes, we equipped them with special spectral filters that allowed us to also see down to the surface of Titan, because we knew ahead of time there were certain spectral regions that would be transparent. You can't see them with your eye, but if you go into the near infrared, you can. And here is an image that we took very early on, soon after getting into orbit. I think it was on our first orbit around Titan. It is contrast enhanced, and it shows that Titan is not like other moons. It's not heavily cratered like Mimas. It's characterized by dark regions and bright regions. We could make out tectonic features in it, and some other pictures taken along with this image. We could see sinuous features that look like they could be channels, but we couldn't really say because we didn't have the resolution to say much. And then came the single most dramatic event in our exploration of Titan, and that was the deployment of the European-built Huygens probe in December of 2004, which encountered Titan in mid-January of 2005 and returned absolutely indisputable evidence of drainage systems on the surface, which indicated either past and maybe even present fluid flow on the surface. This is why we went to Saturn, to see things like this. And then minutes after this picture was taken, came this historic picture taken from the surface of Titan after the probe landed, looking at the horizon. It landed in an unconsolidated medium, almost certainly those haze particles, which eventually grow and get bigger, and they fall down onto the surface. And these cobbles here, I believe they are believed to be made of water ice, and they're about that big. So this was the first landfall in the outer solar system. It was a very remarkable and historic day, something like you might find in a Jules Verne adventure. The Huygens probe told us many things about the surface environment of Titan, but it did not find any liquid hydrocarbons on the surface, not even a puddle. So it became even more puzzling why there weren't any liquid hydrocarbons when the radar instrument I told you about found that the equatorial and mid-latitude regions of the moon were covered by dunes. These are 100 meters high, about 2 kilometers apart. And they completely encircle the globe in the equatorial and mid-latitude regions. Dunes like this, they're called longitudinal dunes. They are created by bidirectional winds, so coming from 2 different directions. And you have to have very dry conditions for dunes to form because you have to loft tiny particles in the air so that they can form these dunes. So they're spectacular. It was wonderful to find them. We've never seen them anywhere else except on the Earth, but there were no bodies of liquid hydrocarbons. And then 5 months after Huygens landed, I'm proud to say my team and I imaged the south polar region of Titan with our cameras and saw this foot-shaped feature here, which we officially called out as the best candidate for a lake on Titan. We called it Lacus Ontario, or Lake Ontario, because it was about the same size as Lake Ontario that separates the US from Canada. And then 12 years later, when the sun had moved from the southern hemisphere into the north, so this was late spring, early summer, we took pictures of the northern polar region, and we found these features here, which again looked very similar to lakes and One of them is in fact called Kraken-Mari. This region, these here are actually connected, and that's what we called Kraken-Mari. If you scaled up Titan to the size of the Earth, this here would be the size of the Mediterranean. And the radar people, the radar instrument, took the following of a different feature in the north, and you could see drainage patterns here, and you could see something that looks like the shoreline of Greece. So later, other instruments on Cassini, like the radar instrument and another one called the visual infrared mapping spectrometer, confirmed that these features are filled with liquid hydrocarbons. So there are liquid hydrocarbon bodies on the surface of Titan. They just happen to be concentrated in the polar regions. So Titan, as you can see, turned out to be every bit as fascinating as we had anticipated. It is the only body in the solar system that has abundant organic materials ponded on its surface, and in its complexity and in its geographical diversity, it is rivaled only by the Earth itself. There are already, because of the excitement brought to us by Titan, there already are future missions that are being built as I speak to return to Titan. And who knows, maybe someday we will drop a boat into the seas, the northern seas on Titan. So the solar system has much in store for those young people today and even those people who are not yet born. But despite all I've told you and all that we found at Saturn, I think the most thrilling and certainly the most significant discovery that Cassini made was what we found capping the south polar region of Enceladus, a moon that is no bigger than England. This, by the way, is not meant to be a threat, so don't get worried. Enceladus' surface is not like the older surfaces of the other heavily cratered Saturnian moons. Instead, its surface is very youthful. There's hardly any craters at all. It shows a very complex array of crisscrossing fractures, and that indicates a very complex geologic history. And the mother lode of discoveries made were found at the South Pole. You're looking at the South Pole, which is about here. And this region is incredibly youthful. There's not a crater in it, which means this surface has been reworked over billions of years. And this region is separated by a chain of mountains that completely circumscribe this cap. It shows a regular pattern of fractures right here, and we found a prodigious amount of heat coming from these fractures and nowhere else on Enceladus. That was absolutely shocking. That would be like finding that Antarctica is emitting more heat than the tropics on our planet. The ultimate source of this heat is the flexure of the moon that occurs because it experiences tides raised in it by Saturn. And it's on an eccentric orbit. So you put the two together and it means the moon's shape slightly flexes, and it would be like taking a paper clip and, bending it back and forth many times, and you feel it and it's warm. That's what is making Enceladus warm. And as if all this weren't enough, when we put Cassini in a position to look over the South Pole in the direction of the sun, this is what we found. We found dozens, in fact 100, jets of fine icy particles spraying from the large fractures. They extend hundreds of kilometers into space, and some of the particles in them go even farther. They go into orbit around Saturn and create what's called the E-ring. And these geysers, we'll call them jets for now, they feed a plume of material that towers over the South Pole. Cassini flew through and sampled this plume about a dozen times. This was one of those things that we planned into the trajectory, the tour of Saturn, executed by Cassini, because we had not expected something this dramatic And so we altered what we were going to do with Cassini to sample this plume. We flew through it. There were instruments on Cassini that could grab up material and measure the chemical composition. And it found that the icy particles in this, I should say these, I don't know if I said this, that what we see in our images is like a frozen mist. So think of water droplets, tiny, tiny, tiny droplets that have been frozen because of it's cold out there. And that's what you see when you see it in our pictures. But it found when the Cassini flew through the plume, it was found that those tiny particles are salty, and they are accompanied by water vapor with trace amounts of both small and large organic compounds, even small amounts of compounds like ammonia and carbon dioxide. All of these compounds are considered significant for life. Images like this one and images like these have allowed us to locate the precise positions of 100 geysers. This is, in fact, work that I did with my own personal research group. And we found, that other teams and we found that the geysers are erupting from a subsurface global ocean that has a salinity comparable to the Earth's. It's laced with large organic compounds, there's available free energy, and all of these are the formal hallmarks of an extraterrestrial environment that could support life. We've even found in the plume hints of hydrothermal activity, which very likely are going on, that activity is going on the seafloor of Enceladus. So Enceladus has now, as a result of Cassini's investigations, has become the most promising place in the solar system to go search for extraterrestrial organisms. And I'm happy to report that in the United States, only just recently, a few months ago, the committee of scientists that was appointed by the National Academy of Sciences, a committee that is responsible for determining what interplanetary missions are of the highest priority for the following decade. It's called the Solar System Decadal Survey Committee. They came forward with a report that placed Enceladus as a #2 priority for the upcoming decade. So hopefully we will get the chance to do a serious job searching for life in the plume of Enceladus. Well, after 27 years as a mission and 20 years in flight, including 13 years at Saturn, Cassini's exploration came to an end when the spacecraft disintegrated in its plunge into Saturn, never to be heard from again. And for the breadth and the depth of its scientific findings, it will surely go down in history as one of the most, if not the most, scientifically productive planetary missions that ever flew. But at its heart, Cassini, like that of all of the story of Cassini, like that of all of our interplanetary missions over the last 6 decades, has been a story about longing, a longing to know ourselves, a longing to understand us. And despite all the strange and wondrous things that we've seen at Saturn, there is one picture that speaks of this longing better than all the others, and it comes with a bit of a backstory that I'd like to tell you right now. Back in the 1980s, I had the immense good fortune of hitching a ride on the most celebrated exploration of them all, and that was the Voyager mission to the outer solar system. And during those years, I had the pleasure of coming to know Carl Sagan and of working with him and others in planning and executing the famous pale blue dot picture of Earth taken in 1990 by Voyager 1 from beyond the orbit of Neptune. And this picture has, over the years, become much beloved, so much so that it and the phrase pale blue dot have become synonymous with an inspirational call to planetary brotherhood and protection of the Earth. Well, since the beginning of my tenure as the leader of the Cassini imaging team, I had in mind to do this picture of Earth all over again, except do it better. And it occurred to me along the way how great it would be if we let the people of the world know ahead of time that their picture would be taken at a particular time from 1 billion miles away, and invite them to go out at the appropriate time, contemplate the isolation of our home planet in the never-ending blackness of space, appreciate the rarity that it is among the planets in our solar system, and marvel at their own existence and that of all of life on planet Earth. And that's exactly what happened. On July 19 of 2013, we turned Cassini's cameras to look at Saturn while Saturn eclipsed the sun, to take another pale blue dot image of Earth, and this time we sent out the word. At the moment the picture-taking window opens, comb your hair, dress nicely, go out, look up, think of all of us, think of the magnificent accomplishment that this interplanetary salute between robot and maker represents, and smile. Smile at the sheer joy of being alive on a pale blue dot. And people responded exactly the way I had hoped. We set up a website to encourage people to describe their experiences, and we received comments, many comments from people all over the world, all over Europe, the US, Asia, Africa, South America, describing a feeling of unity with their fellow Earthlings. And for lack of time, I can only read one. This is what a woman named Jolyn from Upper New York State in the US had to say. I have been entranced by this project ever since I heard about it and was determined to join in the celebration. We stood on the edge of Lake Ontario in upstate New York. I had forgotten to bring my cell phone with its app that shows the location of Saturn, so in the end, we just spun in circles, waving at the sky. They must have looked like crazy people. The thought that a camera was taking pictures from so very far away was just incredible. We may not be unique, we may be transient, we may be only flying along on a dust mote, but for those 15 minutes, we were there, we were aware, and we smiled. And so it was a great success, and here now is the picture. I'm sure all of you have seen it by now. That was taken as this woman and her friends and many, many more all over the globe were thinking about our place in the cosmos, a picture that I called The Day the Earth Smiled, showing the rings of Saturn in the foreground. Of course, you're looking at the dark side of Saturn itself because the sun is behind Saturn. Here is the ring that's created by the geysers coming off the surface of Enceladus. It's the E-ring. And 1 billion miles in the distance is our pale blue dot of a planet, our small, fragile blue ocean planet, Earth. A picture taken while people were smiling in return. There is always something very powerful about seeing our own planet, our home planet, as it would be seen by others in the skies of other worlds. And I think it is that startling, uncorrupted recognition of where we really are and who we really are that never fails to move us. And it moves me to think about evolution. For me, this is the picture where the biologist Charles Darwin and the Italian astronomer Galileo come face to face. Why? Because it is an image that was ultimately made possible by Galileo's first experiments with gravitation over 400 years ago, and it is a picture that absolutely shouts evolution. I look at this image and I see our distant ancestors stepping down from the trees and walking upright for the first time onto the African savannas and pausing to look back at the forest from which they came. And I look at this picture, and I see a species that is positively relentless in its pursuit of knowledge and brave and ardent in its longing to grasp the meaning and the significance of its own existence. And finally, I can't help but look at this image and see the very best that humanity has to offer. We are, without doubt, the cruel and warlike inhabitants of one tiny little dot of a planet, and we are reminded of this day in and day out wherever we look all over the globe. But in those terrible moments of great despair, it would serve us well to remember that we are also the thinkers and dreamers and explorers who took this picture. One world, clear across interplanetary space to another. And to be so small and reach so far is what makes us the extraordinary citizens of planet Earth. And it is this well-earned pride in our accomplishments and the knowledge and the perspective we have gained about ourselves and our place in the cosmos that form the ultimate legacy have made it unmistakably clear that we live on the most beautiful, fragile, and precious planet in our solar system, that there is literally no place else for us to go to survive and flourish, and we must do all we can to protect our planet for our sake and for the sake of all of life on Earth. Thank you very much.
So thank you again, Carolyn, for your wonderful speech about the essence of our life, I guess. Basically, that's what it is. And I'm really looking forward to look back on the pictures. I don't know, are they available somewhere? How can people, again, view these? Yeah, I guess so.
We put every picture that we produced for the public and press releases and lots of information are on a website called cyclops.org. And Cyclops is misspelled deliberately. It's CICLOPS.org because it stands for Cassini Imaging Central Laboratory for Operations. See, I spent so many years working with NASA and the Jet Propulsion Laboratory, I'm an expert at acronyms. And that's what it is, it's an acronym.
So look out, not with a Y, but with an
Cyclops
I.
with an I,
yeah, okay,
.org.
Great. Okay, room for questions. Anyone? There's a catch box here, but anyone who would like, yeah, here, Professor Luiten.
You're not allowed to ask me a question that I can't answer.
Well,
that's
lots of questions. Have to like this? Is this okay? Well, the first thing is this hexagonal shape on the north, the south pole of Saturn. Why is it hexagonal? Do you have an answer?
Oh, okay. If you, I didn't have the time to show it, but I normally show you a movie made of data taken of the Earth, showing what happens to our jet stream. And even there, I think it's variable. Sometimes there's 6, sometimes there's 7 waves. It has to do with, I don't have the formula at the tip of my fingers, but it has to do with things like the rotation speed, the size of the planet, how many waves you get. But it's just really the same thing. It's waves that are created by the motion and so on. And if you took something that it was just sinusoidal, like this, okay, and you wrapped it around a spherical planet, it ends up looking like you've got straight sides and then, kind of smooth boundaries, and that's it. It's nothing, it's like not really mystical.
Patterns on a drum.
Huh?
Patterns on a drum.
I guess so, patterns
Yeah,
on
the
a
standing
dome.
waves, standing waves. That's
Except they actually move. They're not really standing, but it's
resonances, I don't know.
okay, it's just geometry. It's not really mystical. But what freaks everybody out is that it looks like it's straight lines, and they're thinking straight lines in an atmosphere. Some alien put that there, you know? That's what they think.
Okay, thank you.
Okay.
Anyone? Yeah. I come to you. Yeah.
I know it's rather less likely to happen on Saturn than on Jupiter, but have you observed any meteorite impacts?
Yes, onto the rings. We have observed the results of meteorites or, projectiles impacting the rings, and they create little clouds of dust, and we were able to image those. We went looking for them, and we found them. Yeah.
Okay, thank you. Yeah.
We actually also, again, one of these fantastic things I didn't get the chance to show, but there is a low amplitude wave that extends from the inner B ring all the way across the C ring, and I forget how many kilometers that is, 20,000 kilometers of a low amplitude wave, literally like the wave on the surface of water where the ring plane is doing this. Like it's about really thin, but it's doing this. The amplitude, I think, is only a few hundred meters or maybe less. And it's a spiral. It's a spiral in the rings, and these were young scientists working on my team, and they figured out that it was produced by impacts into the rings and probably a chain of impacts, a chain of projectiles that would have been produced by, let's say, a comet, an object that has the consistency of a comet. It came too close to Saturn. Saturn tidally ripped it apart so that it looked like a chain, and that chain went barreling across the rings, and it forced some of the particles to have inclined motion, right? Because it's giving them motion perpendicular to the rings, and that's how, and we think that's how it formed. And we can even place what year it happened. It happened in 1983. So it happened like 2 years after Voyager had visited Saturn. So there's things going on in the solar system all the time. And
Okay, thank you. There's a next question coming up.
Hello, can you tell us about the moon you didn't have time for in the presentation?
yes, okay, it's very good. I knew someone was going to ask me that. That moon, it happens to be very porous. It has a very low density, which means it's very porous. It's kind of like just material gravitationally collected onto this smaller object, but it grew to be a certain size, being very porous. And in a normal, let me back up and say, in a normal surface, like Mimas, which is hard rock you can think of, if a projectile comes in, it hits, makes a hole, it scatters the material out, the material goes in, forms like a skirt around the crater. That's called, what is that called? I can't even think of it now. But like an apron. Okay, and that's the normal, classic set of features for a crater, like on our moon or on Mimas. But when you have a moon that is so underdense, it's so porous, impacts, what they first do is punch a hole, a deep hole. Okay? That's why the craters on that object look so deep, because they're not so much excavating as they are compressing the material that is porous. And where there is material that is thrown out, because that moon is so small and underdense, that debris actually escapes the moon. It doesn't fall alongside the hole created. So that's why it looks the way it does.
Thank you. Anyone else?
Hi, thank you for your presentation. I was wondering, you told us about the agency that determines which space exploration missions are relatively important. And you also said that the moon Enceladus, it was pronounced. Enceladus, it was pronounced, which contained possibly the most vital parts of life, was the second most important mission. What could be the first one?
Okay, it actually was a good choice. I've been promoting an Enceladus mission, meaning a flagship mission, big mission with a lander. You land on the surface. If you land on the surface, you've got the jets, the geysers are going off, these fine particles are going up, but 96% of them come right down to the surface. So all you have to do is like take out your detectors, put them out. You know, it'd be like going out and sticking your tongue out when it's snowing, you know? So that would be the kind of mission we'd want to do. In order to do that, you have to get there when the southern hemisphere and the South Pole are in sunlight, so you can see where to land. But that means that you couldn't really start a mission back to Enceladus until about the end of this decade that this committee considered. So let's say about 2030, you start the mission, you wouldn't get to Enceladus until 2053 because it takes about 10 years to develop, it takes another 10 years or so, you know, that kind of thing. So a mission to Enceladus couldn't really have started until the very end of the decade this group was asked to consider. So they treated Enceladus as second priority, and the first priority is a mission to go back to the planet Uranus and take a probe there that would go into the atmosphere. And they suggested starting that right away. We couldn't have started Enceladus right away, because if we had, we'd get there when the South Pole was in darkness and you wouldn't be able to do it. So it actually was a very reasonable thing they did. I was very happy to see it. The problem is that it's not clear NASA was going to have the money to do it. So we'll see.
All right, thanks.
Yeah.
Okay. Yeah, there's another question.
Hi, thank you for these beautiful images. I'm intrigued by this idea of dropping a boat into this lake of methane. And do you already have any idea of what it would look like? Because I imagine that it might be very different from our lakes and oceans, right? In terms of friction, buoyancy, gravity, temperature. What?
Are you saying how would that lake be different, or what it would look like if you were there?
No, if you were to design this boat, you need to take into account that I suppose that this lake is not, it has very different properties, right? So your design would also look very different compared to a boat that you would design on Earth.
I don't know how different it maybe would have different dimensions. You know, I mean, it has to float. You want it to float. It was kind of a joke to say the Mediterranean filled with paint thinner, but paint thinner is a hydrocarbon, so is nail polish remover. Okay, can you float something in there? You know, design something that would float in a big old vat of, paint thinner, and of course you'd do a better job than that, but that's all you'd have to do. I think it does behave differently. So you'd have to, I don't think it would be a terribly hard thing to do.
Okay, thank you.
Go do it.
Okay.
Quite challenging, I guess, but okay. Who's next? Yeah, here's a question.
Hi, thanks for your talk. Mm-hmm. I was wondering if there are so many moons around Saturn, the effect of gravity on the ring might be chaotic, if it has any effect at all, but I assume it does.
The moons are relatively small. Okay, Titan is the biggest. It's as big as the U.S. All the others are very small. They don't have as much of an effect as Saturn itself does. There is, I think, a slight change in where the plane of gravitational equilibrium is because of Titan. I don't have at my fingertips just how much of a change that is. But so people have considered it. Don't think that it was overlooked. But it's not that big a deal.
So you're saying the rings ever so slightly are turning around Saturn, but the effect is really small.
I mean that where they settle, yeah, precessing maybe, yeah, but I think it's very tiny.
Okay.
Can you say something about the age of the rings and for how long they'll still be there?
Oh, okay. So the age of the rings, that has been debated ever since Voyager days. So some say about a few 100 million years. That's how old they are. That's also about how long they would last. With Cassini, there were some saying, yeah, it could be young, but then the B ring, which is the densest part, has the most material in it. In order to create that, the argument went, you would have to have, oh, by the way, I never got to say this either, but the general understanding of how these rings were formed is that it was a moon, either within the Saturn system that was, its orbit became very eccentric so that it got close to Saturn at times, or maybe a body that came from like the Kuiper Belt and came in, also got tidally disrupted, okay, to create the rings. In order to create the B ring of Saturn, where most of the mass is, you'd have to have a moon or a projectile that was so big that it would have had to be, this would have had to happen very early in the history of the solar system, because that's when you had objects that big careening around. We don't have generally objects that big anymore. So that's what was the argument for old rings. But just recently, in fact, in the last week or two, there's been a suggestion, again, it's just a theory, that there was a moon at one point that was in orbit around Saturn, and something happened that made its orbit go chaotic or something. And then it did a number of things. It came too close to Saturn. It shed its outer shell that created the rings. It also crashed into Saturn and caused it to have the obliquity that it has, et cetera. So unfortunately, you can't really prove any of these things because they all refer to things that happened in the past. So that's the long answer. The short answer is we don't know.
That's an answer as well.
Thank you.
Okay. Anyone? Yeah.
Thank you for your presentation. And I was wondering, so you mentioned the A, B, and C rings, and then the E ring. But what is there a D ring, maybe?
Oh, yeah.
And what is it
okay,
composed,
so,
or where is it?
okay, I showed you the A, B, and C ring. The D ring is inside the C ring, has very, very, very little material in it, but we know it's there. The F ring is a narrow ring outside the A ring. The G ring is further than the F ring, and it's not narrow so much. It's like a puffier ring. The G ring actually is just constantly being created because it's coming off impact. It's created by impacts that come off little moons that are embedded in the G ring. And the E ring is created by Enceladus. So it's not really in a logical order, because it's more has to do with the order of discovery. So we have the A ring all the way out to the G ring. I don't know anything if there's an H ring. If there's an H ring, I don't know about it.
Thank you. And for the E ring then, because in the picture we see that it is lower, so it's not in the same plane as the other rings?
Oh, no, this is just,
or it's just
this is a highly, I mean, it's hard to get a sense of the plane here because you're looking, well, how do I explain this? This is all in the same plane. What, hello? Wait a minute. Just technical difficulties. These are the rings. That's in the same plane as this. I guess I could have just pointed this out. This is, excuse me. This is the outer edge of the A ring. This is the F ring overexposed. It's not really that thick. If we took an exposure that was appropriate for that ring, it wouldn't look this way. But so this is the A ring. That's the beginning of the B ring. This is the F ring. This is the G ring. This is the E ring. and they're all in the same plane. The E-ring, though, is very, if this was the plane of the rings, the A, B, C, D, F ring, and even G ring are all very nicely in the plane. Maybe the G ring is a little bit puffy. The E ring is really puffy, okay? And but they're all in the same plane.
Okay, thank you.
Thank you. I saw a question here. Give it a try. Yeah, you can do it. Okay, nice catch.
So at the end of the mission, I imagine something you've worked on for decades. How did it feel to have it end in a plunge into Saturn and finishing your maybe like life's work or the project you worked on?
I know what you're all expecting and hoping I'm going to say, that I was distraught and heartbroken, and there was my life's work, and I couldn't bear to see it go. And I have to tell you, it was just the opposite. It was like, great. I'm not in the gulag anymore.
Out of the bank.
It was an incredible privilege. I mean all of this sincerely. You can have conflicting emotions all in one person, so here you go. It was an incredible privilege to be in this position. It was joyous at those times when we found things like the geyser basin on Enceladus. I felt like the explorers who discovered the geysering basin at Yellowstone. And all the various things we found, it was just spectacular. I mean, really. And it was also an incredibly difficult job to do. It demanded, for 30 years, it was like living your life on a metronome. We had to plan observations and uplink them to the spacecraft once we got in orbit. That was like, you couldn't decide, I'm going on vacation now. You can't do that. So there's a lot of work and a lot of, I'm afraid to say this, but it's true, a lot of politics. Okay? So I felt, this is the best way I can describe it. There will be those junctures in your life where you know that your life going forward is going to look absolutely nothing like your life to that point. It could be if you're married and you lose a spouse, or you get divorced, or your final child goes off to college and you're now an empty nester. All those, or maybe you come down with an illness, or maybe something really great happens to you. You change jobs, you move to another town. And it's those points when I think all of us just go into this retrospective thinking about, where am I in life, and what did I just live through? And that's the old me now. There's going to be a new me, and it's those kinds of things. And that's exactly what I was feeling. So it was those kind of emotions, like this is a major juncture. But I was very glad that it was over, because it was a lot of work, and I'm retired now, and I'm having a blast.
But your work comes with emotions, isn't it? I mean, at the end of your presentation, when you were leading up to this last picture, I think the essence that the work comes with is moving in a way.
Yes, of course it's moving, because this is like, can you think of anything that a person could do in life that has greater reach? Yeah. I mean, that's what attracted me to this job. And, when you think, well, here I am in my office, but I'm planning something that's going to happen on the other side of the solar system. Yeah. It is very moving. So, and it's very moving to even, go through the tail end of my presentation. I have to tell you, I'm like at 5 places. I'm like, don't cry. Don't cry. Really, it is moving.
And how is that in relation to what's happening on our planet at this
I'm
very
sorry,
moment?
what?
How does that relate to what is happening on our planet at this very moment?
Well, I think it just, I said it. I think it's that kind of thing. When you look at the mess, especially nowadays that we're in, and you can really, I think, man, human beings are a total waste. Look at the mess they've created. But I think about this. I think about all the great scientists and engineers and everybody that brought this kind of thing about. And I think we're just a conflicted species. Like everything else in life, there's good and there's bad. And it's when you're feeling really awful, think about this.
Yeah,
you know.
that's a very good advice.
And it also, of course, my final message is I do really honestly think the greatest legacy of all 6 decades of exploring the solar system is perspective. We really can see, you know, we have that visual that tells us that's us. We are alone in the blackness of space. There is no planet B. Don't listen to people like Elon Musk tell you we're going to go terraform Mars. We're going to go build cities on Mars. I don't think the man has sat down and actually worked out the numbers and realizes how big an enterprise that is, how much it's going to cost, how actually, in essence, it's kind of absurd. And don't think that that is a solution to our present problems. We have to fix this planet.
Yeah, certainly agree. Anyone? Yeah, applause. Yeah, fully agree. So maybe to round off the discussion, a little bit more about the prize that you're going to win. How does that come?
I'm sorry, what? I didn't hear that.
About the prize you're about to receive.
The prize.
The prize, yeah, the reward.
Well, I mean, as I understand it...
because people don't know for what reason it was given.
I'm going to receive a prize from the Sickens Foundation, which is the foundation of the Sickens Company, and they are a paint company.
Yeah.
Okay, so it's kind of odd, like why would a paint company be giving me an award? But they have this prize that goes generally to artists who do wonderful things with color.
Yeah.
So it's great, actually.
Did you know about it?
No, I didn't know.
And you were so excited, you thought that's something I should... that's a reason for me to be in Holland and to receive the prize, of course, yeah.
That's a reason what?
A reason to come to Holland to receive this prize and to have
course,
this lecture.
Yes.
Yeah, it's really nice.
So I guess they gave it to me because I have made a big deal about producing as close as possible to natural color for all the things in the system that have color. And no one in my business ever paid that kind of attention to it. And I know in the beginning they thought I was nutty, my colleagues, like, come on, color, like, you know, we're scientists, we don't do things like that. But I did, and they liked it.
Yeah, of course. Yeah, but how about your thoughts about art and science? I mean, this is a piece of art indeed. Or how do you consider it?
Well, I think art and science derive from the same wellspring. It derives from our wanting to be kind of more engaged with the world around us. You know, I mean, artists try to represent what they see and then try to present it to other people. We try to represent what we see also by means of explaining it. So it's similar, different, but similar.
Yeah, okay, I can understand. Are there still questions in the audience? Are we all happy? Yeah, there are lots of questions. It never ends, but I saw a hesitating...
Oh, I'm sorry. I forgot. You guys are looking at that.
Sorry, no, there's still one question here. Yeah, if you could throw the catch box there. Yeah, marvelous. Yeah, it's out. the black circle,
okay.
The black circle.
The mission is called Cassini-Huygens. So Huygens is a Dutch astronomer. Cassini, how got his name connected to the mission?
Yep.
I can't understand.
The Cassini, the Huygens part of the mission name is well known, but the question was about Cassini, the background of Cassini.
Like who was Cassini?
Yeah.
Cassini, and why is he in the name?
Oh, because he was a 17th century astronomer who did a number of things in science, or astronomy and engineering, but he discovered Cassini's division in the rings. I didn't show you Cassini. Well, let's see.
Okay.
Yes. Can I do this? Oh, yes, I can. This is Cassini's division. It separates the A ring from the B ring. It's the biggest division in the rings, and he was the one who found it. And guess what? A guy named Enki discovered the Yankee Gap, and someone named Keeler discovered the Keeler Gap.
Okay. Thanks.
It's the way it goes.
Okay, I think we could go on for hours maybe, or ages, but I would like to round off, unless you have still some famous last words to share with us. I really would like to thank you again.
Okay,
yeah.
Thank you
Thank you
very
again.
much. Thank you for
Wonderful
coming.
to have you here,
Yeah.
and have a nice stay in the Netherlands, and be happy with the prize you will receive. It's in a lovely museum.
I'm looking forward to
it.
it.
So, thank you, and a nice round of applause again for Carolyn and Porco.
Thank you very much. Staying so long.